I hope everyone can hear me loud and clear. And I'm calling you from Leiden Observatory. And tonight's is astronomy on tap. So the first question I ask myself is what I'm going to talk about. What is the best topic to present tonight? So the first question, I think it must be linked to astronomy, but it also need to be connected to the bigger text. So I come up with the title, The Echo's Origin in Space. Okay, I hope you will enjoy it with the beer, especially the cold beer, because I'm going to talk about an environment with extremely low temperatures. So, let's talk about the echo's origin in history. On Earth, drinking water has been longer than 10,000 years, back into the late Stone Ages. And nowadays, we can find echoes everywhere, right? For example, at your hand, you have beer or glass of wine containing ethanol. And before eating the snacks, someone gets a snack, I hope, in the room, and you might be advised to use hand sanitizer to clean your hand a little bit by some echoes. So how about the echoes in space? I want to show you tonight is where do echoes exist before the star formation, and what kind of echoes we are talking about. Are they drinkable or undrinkable? Most importantly tonight, I want to show you how do they probably form from experimental perspective. Are brains needed or not? Okay, to talk about the echoes formation, we need to talk about a little bit astronomical background, especially the star forming evolution. The evolution of star formation is shown in this beautiful illustrative diagram, starting with interstellar clouds with extremely low gas density and low temperature around 10 Kelvin. In such extreme conditions, the gas species are freely accrete on the darker grains and forming solid-state molecules, and later clouds will collapse to form a protostar hitting the most inner region, as you can see the yellow region here, and remove all the previous formed solid-state molecules into the gas phase. And this is also the region a lot of interstellar organics can be found, including the ethanol and the methanol in the protostars. And because of the conservation of angular momentum, all the rotating material, including dust and the gas, will contribute to the formation of protoplanetary disk with a star at the center, and eventually all contribute to the formation of the solar system, including the planets and the comets. And why I show you this diagrams? Because the recent observation by ALMA telescope toward the low mass protostar and Rosetta mission toward the comet 67P GC revealed a great number of interstellar molecules shown in these figures, covering from the most abundant species like H2O and some volatile species like O2, CO, some organic molecules like methanol, ethanol we are going to talk about today, and even some simplest amino acid like glycine has been detected in the cometary ice. So as you can see, this one-to-one correlation about the species detected in the protostar and comet, and actually these molecules has been suggested they have a common and early origin way before the star formation, probably originated from the interstellar molecular clouds. And actually this conclusion is in line with observation and theoretical calculations. For example, the IR observation has shown the interstellar exists containing some icy molecules like the water, CO, CO2, ammonia, methane, methanol, in addition to the silicated dust grain. So we can imagine that the interstellar ice mantle, like we have a dust grain at the core and covered with different kind of icy molecules. So what about the composition of the ice mantles? So of course, water is the most abundant species in the solid state as well, and followed by the CO2 and other volatile molecules. But we also have some organics like aldehyde and echoes. And echo is the topic of tonight. I will talk about the methanol and ethanol here with some special flavors like sulfur species like OCS-SO2. So if we imagine that the ice mantle is a cocktail, the ice percentage is about 30%. Yeah? So what is the formation mechanism of these interstellar molecules, especially in the solid state? There are two mechanisms. First, the gas phase fraction. So imagine that in the very low gas densities, the gas phase species very in the solid state. So the low gas density means the low collision of these reactants. And even these species can find each other and whether they can survive. Yeah? Especially the exothermic reaction will break up this newly formed product into some fragments. So the conclusion is that it's very, very hard to form hydrogen-rich molecules in the gas phase. Therefore, I introduce you another scenario. It's the chemistry taken on the Dawson grade. The solid state has three advantages. The first one is the Dawson grade provides a third body. It will allow the gas species to accrete on the surface, significantly increase the collision possibility. More collision, more reactions. The second advantage is consider the Dawson grade. It can be the very efficient energy sinks. That means that all the excess energy of the exothermic reaction can be dissipated into the Dawson grade and stabilizing the newly formed product on the surface. The third advantage is the Dawson grade could have a catalyst effect. What is the catalyst effect? That means the reaction taking place on a large surface will be speed up. So compared to the gas phase, we could have more hydrogen-rich molecules can be formed in the solid state. So that's the theory about the molecules formation in the space. So what we can do and how do we study the methanol and ethanol formation in space? So the interstellar ice analogues are prepared and studied in the laboratory for astrophysics and Leiden Observatories. To study the methanol formation, we need to create a vacuum chamber mimicking the interstellar cloud condition with low gas density and cryogenic temperature as low as 10 Kelvin, which is equivalent to the minus 263 Celsius. At such a low temperature, the Dawson grade acting as a third body allows the gas phase species to accrete on the surface and associate form the molecules. The ongoing chemistry on the Dawson grade are monitored through the Fourier transform infrared spectroscopy and by observing the vibrational transition of these newly formed species, which is the technique called molecular fingerprint, and this is the techniques are going to be used by JWST telescope. So the first result I want to show you, because this is the experimental talks, so I might show you some experimental ion spectrum. So the first result, I show you the interstellar ice analogues containing only the pure CO ice. The CO are deposited onto the Dawson grade at 10 Kelvin. The ion spectrum show the vibrational transition of the CO at 2140 wave number is equivalent to 5 micrometers. And when the CO ice deposited with hydrogen atoms, you can see the CO accretes on the Dawson grade associated with the white dot, that is the hydrogen atom. It can form hydrogenated product, for example, the formaldehyde and the methanol. The ion spectrum confirm the formation of the formaldehyde and the methanol by observing their vibrational transition. So what the experimental result told us? The experiment shows that the CO hydrogenation can form the formaldehyde and methanol through the hydrogenation reactions. Hydrogenation means that adding hydrogen atom to the inorganic CO molecules. Along with the hydrogenation channel, we also can add different flavors to the icy cocktail. For example, we also can observe some carbohydrate like the alcohol and the sweet tasting like sugar echoes to the icy cocktails. So now we know how to make the methanol in the space. However, if we look at the chemical safety of the methanol, first, it's flammable, it's toxic. If you combine these two, it will break you. Yeah. So, how about the drinkable ethanol? Ethanol also flammable for sure, but also with a warning sign, which means that don't drive after drinking. Yeah. So very important. It's also one of the take-home messages of today. So instead of the carbon monoxide, we start with isolene. Yeah? Isolene C2H2 is one of the simplest hydrocarbon can be found in the space. So in the ion spectrum, I show you isolene ice deposited onto the Dawson grade at 10 Kelvin. It shows the vibrational transition of these species. And white isolene ice deposited with hydrogen and oxygen atoms, there are several new ion features. appears, and we securely identify as ethanol, acetaldehyde, vinyl alcohol, and ketene. And all these products can be connected through the hydrogen and OH radicals. So what is the possible formation mechanism? So in this diagram, we start with acetylene C2H2. The hydrogenation will convert the hydrogen content of this hydrocarbon. But once we add the OH radical, the hydrogenation of the acetylene will convert to oxygen-bearing species. For example, we can detect acetaldehyde, ethanol. Now we produce the ethanol in space. Let me wrap up today's talks. I show you two recipes to make the ethanol in space. But what is the implication in astronomy? Okay, so in the molecule, in the interstellar clouds, carbon atom are converted into the carbon monoxide in the gas phase. And when the dust rates are low enough, the temperature is low enough, the carbon monoxide can significantly accrete on the surface, associated with the hydrogen atom forming the formaldehyde, H2CO, and the methane. And this is following the so-called bottom-up route from the small species to the big. On the right side, you can see the top-down mechanism. We start with the pHs is a polycyclic amorphous hydrocarbon, and is very abundant in the diffuse cloud. Once the pHs are destroyed by the UV or cosmic ray, will generate the hydrocarbon. For example, like acetylene, we use as a precursor to make the methanols. And both mechanisms, bottom up and top down, are all astronomically relevant, and they can enrich the molecular complexity and contribute to the building block of life, which can be ultimately delivered to an early planet like our Earth. Few take-home message I highlight here. I show you methanol. Ethanol can be synthesized in interstellar ice mantle. With upcoming JWST, more organic molecules will be discovered, meaning more flavors will be added to the ice cocktails. I hope I convinced you today, like laboratory data are important to identify interstellar molecules through spectroscopy, but able to tell their history by studying their chemistries. And thank you for your attention. I'm happy to answer all the questions about echoes.
So are there any questions? Go to.
One on the back.
When you compare the mechanisms at the bottom, in which cases do you get one mechanism and in which conditions will happen? You get which mechanism?
If I understand your question correctly, you mean that which one is more dominant, right?
Yeah, exactly. And in which parameters, like physical parameters, make this mechanism work? Yeah.
Yeah, okay. It's a very good question. I can answer you by quoting Sander Thiele's words. Sander Thielen says, all the laboratory studies are relevant in the space, in the universe. Your question or your challenge is to find where it is. Yeah? Is that a question to you? Is that the answer to you? Sorry. Do you have more question? Sorry, do you have a question?
No.
No? Okay. No worries.
How long do you run your experiments? I mean, I don't know how fast these chemical reactions in the universe are, but I imagine it's very slow. So you have to wait a year until you find the peak or a minute.
Yeah, it's also very challenging and also very realistic questions. Okay, so we are now going to produce ethanol, to produce alcohol, right? We are to sell on the street, yeah? So our goal is not to optimize the production here, right? So our goal is to mimic the most realistic chemistry taking place in the space, right? So we need to consider what is the, for example, for the methanol formation is rely on the H condition, right? So the question we need to ask, how many H do we have? And how long the molecular cloud can survive? And what are the temperatures? Yeah, all these three physical parameters will determine what is the maximum formation yields. Yeah, so we need to address every physical and chemical parameter to decide how long we are going to synthesize this methanol. For the methanol work, normally we perform in 1 day, yeah, because our students need to go home to get sleep and dinners. Yeah.
All right.
Yeah.
So, no more questions? Then, yeah, go ahead.
Do we see methanol and ethanol in the later stages of star formation here that we would organically disappear? Do we still see methanol and ethanol in those stages?
Yeah, I believe so, right? They have observed the methanol in the protoplanetary disk, and they got the Nature or Science paper on this.